what happens at the interface of three different phases? To understand this, we can have a closer look at the sketch on the right-hand side. There's a gaseous phase, a liquid, and a solid. And each of those phases interacts with the other phases. So there's a liquid-solid surface, a solid-gas surface, and the liquid-gas surface. As we've learned in the previous video, all these surfaces tend to minimize their energy. And this results in the forces depicted by the red arrows. So there's a force in direction, a tangential force along the gas-solid interface, along the gas-liquid interface, and along the liquid-solid interface. There will be movement until an equilibrium is reached between these forces. And this equilibrium is then defined by the contact angle theta. If you do now the trigonometrical calculation, you will find out that what is described by Young's equation, that cosinus theta equals to the surface tension of the solid-liquid interface minus the surface tension of the gas-solid interface divided by the surface tension of the liquid-gas interface. However, in reality, it's a little more complicated, because if you look on a micro scale on solid surfaces, you usually have a certain roughness. And this leads to a difference of the apparent contact angle compared to your expected contact angle. So from your macroscopic point of view, you will see the apparent contact angle, which is much larger than the real contact angle. And this is only because of the roughness of your surface. One of the effects of this apparent contact angle change is that liquids can pin and don't move on in microfluidic systems because of surface roughnesses. But let's go back to the theoretical and perfect surfaces. In general, systems consisting of a liquid and solid interface can be distinguished into two different behaviors. The first one is called hydrophilic. And this is always the case if theta is smaller than 90 degrees. The second one is hydrophobic. And this is the case if theta, the contact angle, is bigger than 90 degrees. On the right-hand side, you can see the effect of the contact angle. So if the contact angle is very low, the liquid tends to move along the surface. Whereas with a big contact angle, the liquid is repelled from the surface. And depending on the contact angle, the wetting behavior of your system can be described. So if you have a contact angle of approximately 0 degree, we talk about a completely wetting behavior. Whereas for a contact angle of 180 degrees, we talk about non-wetting behavior. Let's now consider a very simple experiment. On the right-hand side, you can see the general setup of the experiment. So you have a droplet of liquid and a capillary that can inject or remove liquid from this droplet. And what you observe in reality is that if you add liquid to the droplet, the contact angle gets bigger than it is in a static case. If you remove liquid, the contact angle gets smaller than it is in the static case. So in general, you can see that there is a change in contact angle depending of the movement or direction of movement of your droplet. And this is what we call the contact angle hysteresis. And this can be described by the graph on the down side here. So there's a contact angle theta on the y-axis, and there's the volume on the x-axis. In the static case, you have a defined contact angle. If you add now liquid to your droplet, the contact angle gets bigger and bigger. If you remove the liquid, the contact angle moves back to the static case. And if you remove even more liquid, the contact angle moves into the receding state and gets lower than the static contact angle. This consideration is only valid if we talk about static cases. So if you add liquid to the droplet or remove liquid from the droplet. However, it's not valid for dynamic cases when contact angles move along a surface. In these cases, you have to use a dynamic contact angle. And up to now, there are no closed theories to describe contact. We know how to describe the pressure in two-phase interfaces by the Young-Laplace equation, but we don't know how to describe it within microfluidic systems yet, when there are walls and three-phase interactions. And to do so, we need to consider the surface tension as well as the contact angle. We've learned in the first video how to describe the pressures in two-phase systems by the Young-Laplace equation. But we don't know how to describe the pressures within microfluidic systems yet, because there's an additional component, the solid phase. To describe the pressure, we need to consider the surface tension as well as the contact angle of our microfluidic system. Let's have a look at an easy example. On the right-hand side, you can see a capillary of circular square area with the radius r, and you can see a liquid that is colored blue, which is approximately, or which ends approximately at this position. So to describe the pressure that acts on the surface, we need the parameters of the radius of the capillary. We need the contact angle theta. And obviously we also need the surface tension between the liquid and the gas phase. So what we learned last time in the first video is that the Laplace pressure is given by the curvature times the surface tension. In our case, in the 3D case, the curvature is given by 2 divided by r prime. The surface tension obviously is the parameter that we just defined. So how can we calculate r prime in this case if we only know r? This can be done by using trigonometric functions. So what you know is that the horizontal distance to the wall is r. And what we also know is the angle of the contact angle theta. And this means that we also know the angle at this position, which is equal to theta. And this results in r prime equals to r divided by cosinus theta. If we now enter this value r prime into our Laplace equation, we get the result that the pressure difference across this interface is given by 2 times sigma times cosinus theta divided by the radius of the capillary r. Obviously, life is not always that easy in reality, as we don't always have a perfectly symmetric capillary. That's why we look at a little more complex structure of a rectangular channel, where it's really hard to tell what the surface looks like. So it's really hard to get this r prime that we just calculated in the last example. For complex systems, the Concus-Finn conjecture is a good way to calculate the capillary pressure. The Concus-Finn conjecture states that the integral of pressure over interface is equal to the surface tension force at the perimeter P. So what does it mean in terms of equations? You can state it like this: the integral of the Laplace pressure over the area, which is colored or which is highlighted in a light blue here, equals to the integral of the surface tension times the contact angle along the perimeter. So along the lines, the edges of our rectangular form here. And this can be easily calculated with the following equation. So the Laplace pressure difference is nothing else than the surface tension divided by the area times the sum of cosinus theta, so the contact angle of every edge, times the width of every edge. This may sound complicated if you haven't done an example yet, but let's look at this example of the rectangular channel and try to understand what it means. So we have the parameters of the width, W1 and W2, and we know the contact angle as well as the surface tension of our fluid gas interfaces and solid interfaces. If we now enter all these values into our equation, we find that the Laplace pressure of this surface that we don't know the exact shape of is given by 2 sigma times cosinus theta times 1 divided by W1 plus 1 divided by W2. And this comes from this simple equation written here. So the Concus-Finn conjecture is a very powerful tool if you don't know how the surface looks like, but if you nevertheless are interested in the pressure that acts on this surface. All right, let's have a look at the learning goals again. So after watching the videos, you should be able to mathematically describe pressures induced by surface effects. We learned about the Laplace equation, and even for complex structures, you are able to get the pressure by using the Conkes-Finn conjecture. In this video, you also learned about the contact angle. And after watching it, you should be able to categorize the fluid behavior based on it. You know that there are dew and wetting liquids. And you also know that depending on the contact angle, you can either speak of a hydrophobic system or a hydrophilic system. The last learning goal, the calculation of the filling time of simple microfluidic structures, will be done in one of our examples. And to do so, you will need something that you learned at the start of the lecture, the Hagen-Poiseuille law, and you will need the capillary pressures that we just derived. Thank you for your attention and see you in the lecture.